Hi. Okay, so I wanted to talk about what is the component effect vector? Like, just instinctively, what is the purpose of them? What do they mean, right? Without getting into the numbers too much. Okay, so basically, the in the last video we said that we need to convert vectors into their components. Okay. And the reason we need to do that is because these two vectors are at different angles and I can't add them the way they are. I have to manipulate them and not modify their value, but modify the way they look so that I can actually do math with those numbers. Now, I want you to know is what does a vector actually, what does the component actually represent? So when I say the x component of this force 1, what am I talking about? So that's about this video, okay? So I'm going to redraw very roughly the oops, wrong color. I'm going to redraw this vector. Um, I'm going to try and make it look similar, but anyway, I'm doing it by hand. So force 1 is equal to 46 newtons, and the angle it says is 35 degrees, okay? So um, I want to talk about what are the components. Okay, imagine, I want you to look at this. This represents a force, and I'm going to just, let's, for a moment, imagine that I'm going to erase that value, and I'm going to write that this is actually 46 meters. Okay, so instead of talking about a force, imagine I'm talking about a displacement. Okay, I started at this dot, and then I walked all the way along here, and I ended up 46 meters away in a straight line at an angle of 35 degrees compared to north. Okay, so one way of thinking that what a vector represents is how much of that total movement is actually happening in the north-south direction. That would be the y component of that vector. So, or the other component, the x component, which would be left, right, or west, east, um, the x component would be, oh, Mr. Broomfield moved 46 meters at that angle. How far to the west did he move? And that's one way of looking at it. Uh, and that I think most people get because we've all measured distances and stuff. We're pretty familiar with it instinctively. A different way to look at it is, and this gets a little more interesting, but is imagine we're back to a force. So force 1 is 46 newtons, right? Now, imagine that this force is being applied. And imagine that this force, somebody's pushing or pulling, it doesn't really matter. And they have, let's say there's a train here, okay? So I'm looking at a train from above, and this train is on a set of train tracks, okay? So as you know, trains hopefully stay on the tracks. So they only move in that one direction. They can move either to the left or to the right. This train hopefully isn't moving up on the screen because it would mean if the wheels stay on the tracks, it would basically tip over, right? So we're limiting the movement of this cart in the left-right direction. And now I'm saying, what if I apply this force to this wagon? Okay. Well, let's look at a couple of situations first, okay? So let's imagine that a different force. Let's do a different color to make sure that it makes sense, okay? Imagine that I go and I pull, I'm going to put it to the side, but I push that train that way with 46 newtons. How much of those 46 newtons are actually helping it move in the XY direction? And the answer is 100%, right? The full value of my force is actually helping it move along the tracks. Let's look at a different example, okay? And let's say I'm going to put it above, but I decide I'm going to push it perfectly upwards with 46 newtons. Okay? And I ask you, what percentage of my force is helping it move in the X direction? And you would look at me with a funny face and say, well, it's kind of pointless to push it sideways when it can, sorry, up down when it can only move sideways. So actually 0% of your force is helping it move, right? And then you have varying degrees in the middle of those, right? So for example, if I did a force that was really shallow, really close to sideways. So let's say, I don't know, let's say that's 10 degrees, okay? Well, you would instinctively think, well, wait a second, nearly all of my force is helping it move sideways to the left, but not quite as I was pushing like the green arrow perfectly along the tracks. I'm wasting some of my force because part of this force is pushing it upwards. So here I would have a percentage and it would be close to 100%, right? Because it's very close to the X direction. So I don't know what that would be. But let's just say I'm inventing this. I'm going to say 95% of my energy, my force, is actually pushing along the tracks. These forces, you could think of it like wind. Imagine there's a wind and the green on the day for the green stuff I wrote, the wind is pushing along the tracks and all of it helps the train move. Imagine the next day, the wind is pointing in the yellow direction and the train, I mean, you could have a hurricane wind. It wouldn't help the train move along the tracks, right? If the wind was perfectly in that direction. And then another day, the wind is along the red direction. And it's like, well, it's not going to move as quickly as in the day with the green direction, but close. So I'm going to get about 95% of my pushing force. So when we look at the numbers, let's look at this. When this, in the green, the full 46 newtons would actually be pushing in the X direction. So the force in the X direction would actually equal 46 newtons. If I look at the yellow situation, the force in the X direction would actually be 0, right? And if I look at the red situation, the force in the X direction would actually be 46 times 95%. 95% is the same thing as 0.95, right? 0.95 times 46, right? If it was 1, it would be 100%. So 0.95 times 46 would give me 0.95 times 46 would give me 43.7 newtons. Okay, so 43.7 newtons of the 46. I'm pushing with 46, remember, in all these situations, but only 43 of those 46, or nearly 44, would be pushing in the X direction in the red situation. That X value, that Fx, okay, here, I'm going to highlight it. That Fx, really cool program this, I love it. That Fx is the component of the force in the X direction. So this right here is the actual force, right? But the component in the X direction is how much of this is actually moving sideways. And if you look at it, it would be something like that. That would be the Fx of, actually, that would be the force 1 in the X direction. That's the X component of force 1. And graphically, you can actually, you can do it mathematically with the formulas that we're using, the cosine and the sine and so on. You can actually do it with a ruler and a protractor. And I didn't measure this angle accurately, okay? I didn't use my protractor to draw this vector. But if you draw this vector at 35 degrees and you actually measure this at a scale of, let's say, 44.6 centimeters, Every centimeter would be 10 newtons or something like that. And then you draw it perfectly at 90 degrees there, and you measure the length of this. Okay, you convert it back, you would actually get the value. So the shadow onto the x-axis would actually, the length of that shadow would give you the value of the x component. So there's really two ways to calculate it. We're going to do the calculations later. For now, I just want you to know what the x component means. The x component is the portion of that vector which is acting in the x direction. The y component would be the portion of that vector which is acting in the y direction, right? It would be somewhere there. Okay, so that would be along here would be F1y. Okay, so instinctively, I just wanted you to know, what do those components represent? Later, where we're going with this is, like, why we use this is, we said earlier, we cannot add these two forces because they're at wonky angles to each other. So what are we going to do? Well, it turns out that mathematically, if I take that, whoa, that was terrible. If I take that vector, okay, I'm going to try and draw it here. Okay, there's F1. And I find the components, that vector in that direction is equal to the x component. So let's draw the x component. Let's say there's our dot, and the x component is about that much. Okay, F1x equals whatever. And I find the y component of this. So it would be an up-down force, which would, if I start here, it would go up to about here, let's say. Okay, F1y. It turns out that this vector is the exact same thing as this vector plus this vector. Okay, so basically it describes the same thing. I can draw a force using this notation with this and an angle, right? Which in our example is 35 degrees. Or I can break this apart into two vectors, one along the x, one along the y, that when I add them, I end up with the original. So kind of like with the fractions, we try to find the common denominator. What we're doing mathematically to add vectors is to break each one of these vectors into two vectors, which together mean the same thing. But now these vectors in the x and y, I can do math with those. If all my x's are along all my components for x are along the x-axis, they're in a line. I can add them. And then I can take all the y components of different vectors and I can add those because they're in a line. And that's where we're going with this, okay? So hopefully this clarifies what the component of a vector is. If you have the full vector, the component is the portion of that which is acting along the x direction, or for the y component is the portion of that acting in the y direction. And if I find the x component and the y component, if I take these vectors, if I take that vector, and I add those vectors, that is the same thing as having the original. So it's two different ways to represent the same thing. I can draw a vector like that, or I can draw a vector, I can break it apart into two pieces, and they are exactly the same thing. So I use this mathematically to my advantage. When I need a vector in a weird angle, I use this way. When I need to add vectors, I break them apart and I get this. Okay, I hope that helps.